Oh, it's not on. Yeah. All right. All right. So I'm a collider physicist. I'm an experimentalist. So I work on CMS experiment. Just to prelude. And I'm gonna put together some lectures on dark matter accelerators. I'm gonna start with the LHC, but it's gonna go in a few directions. And certainly based on your guys' suggestions, I can go in different directions. I probably have more than enough material for I could probably, if I go slow, I could probably do 10 lectures out of this. So there's plenty of material here. So just ask as many questions as possible. Yeah, so let me start this talk in 1845 in Berlin. I don't know if you guys know this story, but Bessel, Friedrich Bessel, was looking at some tables of series. And Bessel was a very precise person. And he was noticing that something was not right with Sirius. He looked at his sky tables and things were moving. And if you just look at Sirius, he actually would see that over time, it was wobbling back and forth. And this is the first time I know of where somebody actually said they had presumed there was some sort of dark matter. He called it unseen matter, right? So Bessel predicted that there was some unseen matter that was actually causing Sirius to move. So what happened? Well, this idea kind of caught hold of a lot of people. And there was another unsolved problem. It had been an unsolved problem for 50 years. And it was actually based on Bessel's tables, right, from the observatory in Berlin. And some people in Paris, in particular, a descendant of Laplace, or one of Laplace's students. Well, I don't know if he was a student, but he worked in Laplace's lab. This guy, Urbain Le Verrier, was trying to do a calculation to understand the motion of Uranus. And Uranus's motion was not understood at the time. And in fact, this had become an open problem in the field. And a lot of people were starting to ask this question. So at the same time that Urbain Le Verrier was doing this, actually, a physicist in London, John Adams, he was actually working on this as well. And they both were trying to come up with a way to explain the motion by adding a dark body, right? And so Urbain Le Verrier, he put a dark body, he tried to move it around and see how he could explain the motion. And he came up with this explanation that there had to be some sort of object behind Uranus. John Adams, ironically, he managed to get to the same conclusion. He was a very antisocial character. And so, in fact, he took the calculation. He was afraid of, I don't know exactly what happened, but instead of publishing it, he wanted to give it to somebody who could look at it. So he went to Airy, I think it's John Airy, Airy Function Airy, who ran the Greenwich Observatory. And he knocked on his door. He went twice, supposedly. And the second time, he actually shoved the manuscript under the door. And so he did that. At the same time, Le Verrier had finished the calculation, and he'd given it to Laplace. And Laplace was like, "We know exactly what's going on." They mailed the coordinates to Berlin, to the observatory outside Berlin. And they actually they pointed the telescope, and the day they got the coordinates, they had discovered it, and it was Neptune, right? And so this is the first known theoretical physics discovery. It's also, I say, the first time we discovered dark matter, right? You could question, but this was kind of a dramatic result, right? In 1846 is when it finished, and it's pretty amazing. Now, what about the first kind of prediction for dark matter, from Bessel? Well, Bessel unfortunately didn't get to see this resolved. He actually died in 1846. But what happened actually was in 1862, actually just outside in Cambridge, Massachusetts, it's actually where MIT is right now. There was a telescope manufacturer. And this telescope manufacturer, he he actually is not a scientist, he's an engineer. He had come up with a scheme to make refractive telescopes, and he was making the largest telescopes in the world at the time. And so he just finished a telescope that was commissioned for him. This actually became kind of the telescope that's now it's at Northwestern. It's they have an observatory there. And he had just finished it, and so he wanted to test it out. Well, why not point it at the brightest star in the sky? So he pointed it at Sirius, and he saw Sirius, but he also saw this thing, this white dot for the first time. So he had no idea what was going on. So the next day, he walked over to Harvard. MIT didn't exist at the time. This is in 1862. So he walked over to Harvard, and he went to an astronomer there. And the astronomer knew exactly what was going on, right? This had now been an open problem for more than 15 years, the motion of Sirius. And this became the discovery of Sirius B, right? Which was actually the first binary star system that we ever discovered. And so this is really a story of the case where technology actually preceded theory or preceded physics, and it allowed us to observe something that in the end became dark matter. So it was a feature of basically just an accident, right? Dark matter, something that we thought was dark matter. And just, just to show you, it actually, the telescope observatory was here, and this is Cambridge. This is just a small part of Cambridge. My office is over here. So I always like to think that the first dark matter problem was discovered in Cambridge, right? Near MIT, so. All right, but you guys all know the dark matter problem. I'm not going to explain it again. I'm sure you've been looking at all these plots. So this lecture I'm going to talk about the case for colliders. So I'm going to start first with kind of how do we search for it at the LHC. I do work on, say, a few accelerators these days, but my focus traditionally has been with the CMS experiment in the LHC. And so I'm going to talk about how we've kind of built up the dark matter searches over the past few years and how we interpret them and how these actually play a role kind of in the world of dark matter searches. I'm going to then so that's going to be kind of the first lecture. I'm just going to introduce the dark matter searches. The second lecture, I'm going to talk more about how do we interpret them. What's the kind of phenomenological foundings of how we interpret dark matter? How do we embed these into kind of full, complete models, right? We typically use these simplified models. And then I'm going to talk about how collider searches compare with the rest of the world, so the rest of dark matter searches. And then in the later lectures, I'm going to go full dark sector. So I'm going to talk about the dark photon bonanza that's going on right now. So you guys, I'm sure you guys have heard of dark photons. You probably heard of another 30 experiments and why everyone is special. So I'll talk about all of these. And then I'm going to go and talk about some of the more exotic stuff and some of the kind of crazy ideas that are going around, and in particular, the kind of rise of long-lived particles. All right, so let's start with the collider and look at how we search for dark matter at a collider. I'll skip this. So how do we detect dark matter? Right, so to detect dark matter, it has to interact with matter somehow. So we need some way for it to interact, right? And so if we need to have dark matter kind of change some way. And the traditional way to do this is to add an interaction. And so the way we're going to do this, I think every lecture, yeah. Well, kind of the way we're going to do this is we're going to not just add one particle, we're going to add two new particles. We're going to add dark matter, chi, and sometimes it's Majorana in my slides and sometimes it's not. So you can go ahead and complain all you want. But yeah, there's going to be high bars. It will change. And then we're going to add a mediator, which I try to call phi, but sometimes I call it z prime, sometimes I call it a. I'm sure you guys are familiar. So, and this mediator is going to talk to the rest of the node users. So this is going to talk to the standard model, and it's going to talk to dark matter, and it's going to connect these. And I think with the exception of dark matter, the case where the mediator is either a Higgs boson, and it can in principle be a Z boson, I'm always going to add two new particles to the standard model, a mediator and a dark matter. Sometimes I'll call this the portal mediator. I mean, it's just a new mediator. So how do we actually probe then dark matter in this model? Well, we do it with the classic diagram of dark matter interacting through a mediator, interacting with matter. And there's basically 4 ways you can do it. You can either break it, shake it, make it, or bake it. It's the easy way to remember this. So how do we break it? Actually, how do we shake it? This is kind of the classic way to search for this. This is what we call dark matter direct detection. So you typically do it at a mind near you. And you have dark matter in the solar system, and then it collides off a nucleon, right, and recoils. And then you measure the recoiling. So, and this just comes from dark matter nearby. And we get plots like this. And I'm going to show you hundreds of exclusion plots in my talks. And pretty much all of them are going to have an x-axis, which is the dark matter mass. And sometimes this could be the mediator mass. But I think the x-axis is pretty constant in these plots. And it will be in units of GeV or MeV. And then there's going to be some y-axis, which could be either mediator mass or cross-section. For all practical purposes, I think I'm going to just show the same plot hundreds of times. But in this case, right, this is just the cross-section exclusion. And in this case, we look for a bunch of lines. So this is a slightly older plot. So we have exclusions here, and then we're excluding cross-sections above this. It's a function of dark matter mass. And just as a note, in all of these plots, there's usually some other thing. So like in this case, we have this yellow guy. And this is the neutrino wall, right, where direct detection becomes maximum sensitive. And that guy is going to play an interesting role later on. So, all right, we shake it. Now, how do we break it? So this you saw in Tracy's lectures, I'm sure. You can take dark matter and annihilate it, produce a mediator, and the mediator decays to something. I put some quarks here, but it could be something else. Could be taus, could be muons, could be, something. And these things are typically excited. And so then you get a shower off of these. And this shower eventually leads to something stable, which could be photons, electrons, or protons, or any of those things. And then you look for this with the satellite, right? And this is what we call indirect detection. And this is typically done at a galaxy near you. All right, and the other thing you probably know, especially since Tracy gave a talk, or many talks, is that you have a lot of exciting things, in particular this galactic center excess, that some people could potentially be dark matter, but could potentially be pulsars. But it at least gives you kind of a benchmark for things to look for. And with that, you make plots like this. Again, the axis here is dark matter mass, like we had for direct detection. And the y-axis here, instead of cross-section, it's a thermalized cross-section, right? And you get an exclusion where you have some sort of line, right? And above that line, you exclude the thermalized cross-section. And then you get things like this, like these circles here, where you have potentially a galactic center excess. And it's at the moment neither excluded nor discovered per se. So, but and then the other thing you have, so like you had with direct detection, where you have the neutrino wall, you have this dashed line here, right? And this is your thermal relic cross section. And so this you get from evolving the universe and looking at the CMB spectrum. So, all right, we make it, break it, shake it. Oh no, sorry, we braked it and we shook it. So now we can bake it. And so the idea for baking dark matter is you treat the universe as an oven, and you go early to the universe when it was hot, and you can look at the relic density, and you can look at the distribution from the CMB spectrum, and you can use this to infer dark matter-matter interactions. Right? And this, of course, shows up in basically every plot. We always find ways to put this in, and so you have a dashed line here, right? This is your thermal relic cross section. And this we get it from actually WMAP observations, right? So you can get this just from the expansion. All right, so finally, let's go back to breaking it. We have dark matter producing a mediator decaying to matter. We can rotate this guy by 180 degrees, and now you get it to make it. And this is what I do at LHC or at another accelerator. And you have quarks annihilating to produce your mediator that then decays to dark matter. And this is effectively what we try to look for at the collider. But it's a little bit trickier than that because we have to have some sort of interaction because this is decaying to dark matter and dark matter doesn't interact. So effectively, this is just a nothing decay. There's nothing. So you need something else to actually look for nothing. And so we have to have some additional signature. All right, so this brings me to the LHC and how we actually search for it. And I'm going to spend most of this talk focusing on the monojet search, which is kind of the conventional way to look for dark matter at the LHC. But then I'm going to kind of, in the last part of the talk, take the same conceptualization of how we search for it and apply it to basically every other object you can think of. So it ends up being not just monojet, but mono, whatever you want. So how do we do this? I'm going to show you this with the CMS detector. And just as a note, right, CMS was not designed for dark matter, at least the kind of dark matter we're searching for these days. CMS was designed to find the Higgs and potentially SUSY. That's what people were excited about 15 years ago or 20 years ago when they designed CMS. So we've had to kind of retool it to do it. What do we do with CMS? Well, we collide things right in the center here. And you have all these different colors. And these are all different detector technologies, right, that allow us to reconstruct particles. I won't go into the details of how you do that. I'm sure you guys know. If not, you can bother me. But in the end, we get a collection of 5 particles. So muon, electron, charged hadron, neutral hadron, and photon. Charged hadron, we always assume is a pion. It's not necessarily the case, though. Neutral hadron, we assume is neutron, but again, it's not necessarily this case. It's just a prior the way we reconstruct things. And we typically have kind of busy events. So here's a plot where we take, so you take the whole detector, right? And we like to take a 2D surface, right? Bounding the detector and unroll it. And then this gives us coordinates. And you know, if it's a sphere, right, it's theta and phi. But we use relativistic coordinates. So instead of theta, we use eta, and then we use phi. And so you can unroll this and you can make plots like this. And this is just the energy, right, as a function of eta and phi. And these are just actually summing particles in grids. This is a heavy ion event, so it's a little busy. And then you can have kind of excited pieces of energy. So like this thing here, which is a jet. And this is just a collection of particles, right? So we reconstruct these as particles. We then look for clusters of particles we call jets. Jets typically correspond to energetic quarks or gluons in the event. And you know, it's one of the kind of building blocks that we use to kind of reconstruct events at the other side. Yeah?
I'm only familiar with the way the Atlas does this, but does CMS also use like a tower and prime tower sort of?
Yeah, so Atlas for some odd reason doesn't use particle. Well, they have particle flow reconstruction, but they typically don't use it. And it's a long debate why they don't. But effectively what they do is they have a so-called, so they look at the different detectors, right? So so they have kind of, you have like 4 detector technologies. These detectors here, the green and the yellow, are electromagnetic hadronic calorimeter. So that look for electrons, photons, and hadrons, like pions, neutral hadron, neutrons, etc. And you can sum the energies of hadronic and electromagnetic decays there, and you can use that to look for clusters of energy, etc. In CMS, we tend to go one step further and look at these in terms of particles. So we link all the detectors together into particle objects. And so we basically deal with a collection of 4 vectors, right? But you can look at this as collections of energies and directions, and effectively it's still looking at 4 vectors, but not as sophisticated, but has its advantages. Okay, so this is all I'm going to talk about in terms of reconstruction of collisions. I'm happy to answer more questions about this. That's what I spend 90% of my time working on. But the rest is about kind of how we interpret the collision. So how we're going to look for dark matter, we're going to look for the case where we have quarks annihilating, producing a mediator, and then the mediator decays to dark matter. So this thing is, the dark matter is not going to interact, it's going to escape the detector. And we're going to have something to identify this mediator. Well, it's going to have to recoil off of something. The simplest thing that we can add is a gluon, right? And this gluon will typically be high enough energy that it will get us a shower of particles. So we're going to get a big collection of particles. And that's going to make what we call jet. And so we're going to look for a jet, and then we're going to look for a mediator recoiling off of this jet. So how do we look for this? Well, we look for a signature like this, right? So we look for a single jet and then nothing else in the event, right? So there's just this is what we call a monojet. So it's just an isolated collection of energy and then nothing. And so effectively you end up with something like this. So if I were just to look at like a 2D slice of this, you have energy, nothing. And what we can do is we can take all of the particles in the event and we can merge them into a single vector. So all of the visible particles, right? So this blue guy is going to be the sum of the visible particles. And in the transverse plane, so assuming we collide along here, right? In the transverse plane, we have conservation of transverse energy. We don't have conservation of longitudinal energy, and that's just simple. When you're colliding protons and you collide quarks, you have no idea how much energy a quark has in the proton, right? It could have a high protonic fraction of the proton. It could have a very low protonic fraction. It's typically like a 1%, right? So it's a small amount. But in the transverse plane, everything is conserved, and so that means that the dark matter is going to be conserved with the matter, and so you just have conservation of transverse energy, and so you can solve for the dark matter by knowing the matter, or in other words, to find nothing, you have to reconstruct everything. So this is kind of the adage that we use for everything in terms of dark matter searches. We basically absorb all of the collisions into a single vector in the transverse plane, and then we look for dark matter. The problem is that there's a lot of backgrounds, right? So in addition to making it, there's a lot of things that like to fake it. And the classic one that we have to worry about is the Z decaying to neutrinos, right? And so the neutrinos are not going to interact with the LHC. Yeah, question?
Is there a question on the cylinder slide?
Yeah.
Wait a second, we need the microphone.
With the eyes.
Yeah.
So this is spatial, right? So what determines how far the jet appears from the collision?
Oh, where it is here
Yes.
relative to this collision. So
Yeah.
that's so in the transverse plane, right, everything's conserved. In the longitudinal plane, it's not, right? So this is just going to be the relative fraction of the proton each energy has. So you can have a jet like go along this direction. It could be very, what we call forward, right? Or you can have it be central. There are correlations, right? Heavy objects have to be central because they need to take more momentum from the proton. But typically there's no kind of, there's, based on your knowledge of the proton's partonic distributions, you kind of know roughly where a jet will be. And the fact that if you're looking for heavy objects, it needs to be central. But beyond that, you don't really know, right? So the idea is to kind of instrument this as far forward as we can. And so what happens is actually in the cylinder, right? These grids are actually a proxy for kind of the density of the instrumentation that we have. And we can typically go down to like this kind of vertical eta 5. So it's a delta theta is something like less than a degree from the collision, the beam axis. So
And then where does the dark matter appear in this?
the dark matter is going with this green line. So it's recoiling up here. So in this case, the matter is going here, the dark matter is going there. So, and just as a note, right, I had to go back to a collision from 2011 to show this, because these days we don't collide one proton at a time. We typically collide about 80. And so what we actually do is we have 80 collisions overlapping. And we look at all of them separately, and then we try to find a collision that's imbalanced, right? And I mean, it's not the point of this lecture series, but separating out all these collisions is a fun and interesting task.
Thank you.
Okay. All right, so now we have this problem where we have things that bake it, so Z bosons decaying to neutrinos. And this we can also use missing transverse energy to at least understand them. So if your Z is decaying to neutrinos, you get recoiling objects on the side. And the missing transverse energy, which we're going to define as the negative sum of everything in the event in the transverse plane, that defines a variable we call met. And the met for Z decaying to neutrinos is just going to be all of the objects that the Z is recoiling on, right? So this is just going to be the sum, the negative sum, right, of the Z recoiling. And we also know effectively that this is, if you add the neutrino PT, this would be equal to 0, right, if these were visible. But since the neutrino PTs are not visible, you just have that your met is equal to the negative Z boson PT spectrum, right? And so if we want to understand the background, Z to neutrinos, we need to understand the production of Z as a function of transverse momentum. And so effectively, the whole analysis is trying to understand the boson PT spectrum. So here we have the missing energy. So this is actually our search. This is an old search, but it's my favorite one. And then Z decaying to neutrinos is your dominant background. So that's what this light blue, purple color is on the top. And so the idea here is you have some data. You have lots of events. Right? This is events per GeV. So these are big bins. So you're talking about hundreds of thousands of events, right? And you have the Z to neutrinos on top. And what you want to do is you want to predict this spectrum. This spectrum is, in this case, the missing energy, but it's also the Z boson PT spectrum, right? And so the challenge of this analysis is predicting the Z boson PT spectrum and then looking for a small deviation on top, right? Your dark matter is not going to have the same spectrum as this, right? If your dark matter is heavy, heavier objects tend to have a flatter spectrum. So here's a heavy object. This is a dark matter with a vector mediator, right, at a TeV. And its spectrum is not going to be like steeply sloping. It's going to be kind of flat. And in fact, the heavier you go, the flatter it gets. You also can have dark matter from other sources. So this yellow guy is Higgs to invisible. So imagine your Higgs decays to dark matter. And again, right, it's actually not produced like a Z boson. So its slope as well, its PT spectrum will be different. So the strategy is to understand this spectrum as well as possible and then look for a deviation on top, right? And so that's what the monojet analysis is. So the idea is to find the Z to neutrino spectrum and then look for a small amount of signal on top of this. And so we want to fit the data. Yeah, questions?
Thank you. Go for it.
Thank you. So, well, I think here we assume only that the mediator is heavy, so that we look at the high MET spectrum, right?
Not necessarily. We don't make any assumptions about the mediator.
Okay, but I would imagine if the mediator is lighter, wouldn't we then look for the signal in the lower ET?
That's right. That's right. So I'm in this picture, I put the signal here, but in reality, this signal can move all the way along, right? So this is just an illustration, right? So, but in fact, we search for dark matter with the mediator mass all the way down to 10 GeV, and that's, I mean, it's going to take me 2 hours to get there, but I'll get there. Yeah.
Okay. Was that plot that you were showing on the last slide made from data, or is that theoretical?
That's data. Right. So, in fact, yeah. So I'll get back to that plot in a second. So let's look at the data. So this is actually the first. If you just take your simulation and your data at the LHC out of the box, this is what you get. So you get some prediction for Z to neutrinos. You have other backgrounds as well. You have a W that decays to a lepton neutrino, and you lose the lepton. Right? This happens all the time. And so you do have that. This is about 30% of your background. And then you have other backgrounds as well, right? Top, diboson production, QC, etc. And so if you just look at the data and your simulation out of the box, you get something like this. Your data looks like this, and your simulation looks like that, and they disagree. If you look at this ratio plot, they disagree on the order of 10 to 15%. It doesn't really agree well. So how are we going to look for a tiny signal, fractions of a percent on top of this? Well, the strategy is to fix all our simulation. And the way we're going to do this is we're going to play games of trying to understand these distributions of data, correcting our simulations and iterating. And we're going to do this all simultaneously and we're going to insert dark matter into our assumptions. So let me explain how we do this. But just to kind of get you excited, we go from this 10, 15% disagreement to this kind of level of agreement, right? And just this range here is from 50% in these points are 0.5 to 1.5. This guy is 1.1 to 0.9, right? So the kind of predictions you can get are the sub percentage level. So let's go. How do we do this? Question?
Yeah, thanks. Where do those leptons go on the W to lepton-less neutrino? Why aren't they seen?
So most of this actually is W decaying to tau. And then the tau doesn't get identified because it just looks like a blob. Like if you have a tau to like a low energy pion, you don't identify it, and it just looks like a strange missing energy event, and you can't remove it. So usually we veto leptons, right? But sometimes they're just not, your lepton idea is not perfect, and so you just end up with leptons. Okay, so the way we're going to do this is we're going to take a control region, and then we're going to have our signal region, which is the one I just showed you. And we're going to use our control region to model the data Monte Carlo distribution, the deviations, and we're going to apply it to the signal region. Now, the nice thing about Z bosons is that they decay to a lot of things. And so we can make a control region where we just take Z to neutrinos. So instead of looking for Z to neutrinos, we can look for Z to muons. So we just take Z to muons, we remove the muons, and now we have a nice Z to neutrino event. Actually, what we do for the W, same idea. These are W, to model the WPT spectrum, we had a W where we lost a lepton. We can just take W events where we have a lepton, and that's a different region. So we just take W to lepton, and we use W to model W, and Z to model Z. So we're modeling the same production process. And here we can model the PT quite nicely, right? So you can get a lot of clean events, right? Here's your Z to muon, here's a data apply. And you can see there's some backgrounds, but they're very small. And so you're going to end up with a plot like this. And what we're going to do is actually every bin in this plot on the left is going to be mapped to our signal region. So the right is our signal region. So you can see the green now is Z to neutrino. So I keep changing like years of plots and data and etc. But I'm showing the same plot in the end. It's always missing energy. Note for the Z to muons, right? We're removing the muons. So we're looking at what we call the recoil. U is what we call recoil. So you can see the recoil. And then what we do is we actually take our simulation and we float it. We add a freely floating parameter that allows us to correct for the data Monte Carlo disagreement. And we take this freely floating parameter and we apply this as a scale factor to our Z in the signal region. So effectively, we're doing a simultaneous bit in the control region and the signal region. And each one of these bins is a freely floating parameter that's attached to the signal region. Right. So we've gone from adding a fit to having about 30 freely floating parameters. Yeah. Question?
Yeah, I was wondering about like the role of Monte Carlo. So do you simulate each of these possible decays and then you just count the tracks that fall along that simulation? And this is
That's right. That's right. So we make separate simulations for all of these guys. We run our selection, right? And then on our simulation, we run our selection on the data, and then we compare data and simulation.
But I missed the reason why there's a discrepancy. Is it known or is it?
Yeah, so the reason for this discrepancy happens to be the way we model Z boson production, right? So the calculation for Z boson production is actually quite complicated. So we're talking about Z plus a jet. And so you have to calculate the recoiling jet PT spectrum. And it's not just plus a jet, it's plus 2 jets, 3 jets, 4 jets, right? And then you have to calculate the spectrum, you have to resum it, right? You have to add all that higher order diagram. And we can predict it pretty well to the few percent level. Also, our simulation is not perfect, right? We don't perfectly simulate the calorimeters. We don't perfectly simulate track reconstruction. We don't perfectly simulate these particles at all, right? So the best way to do this is we make the best simulation we possibly can, and then we compare data and simulation, and we apply a scale factor, right? And then the strategy is, how do we make a scale factor that's close enough to our signal region for us to trust it, right? And Z to Z is a great scale factor because, you know, Z boson should behave the same no matter what it decays. But this, of course, is not necessarily the best thing. So we do start with this, right? We take a ratio of Z to muons to Z to neutrinos. But we want to add more things. Actually, just to illustrate what I mean by scale factor before I go to the next topic, is every bin here is constrained. So you can imagine you have a signal distribution, you can imagine you have a background distribution, and your background here, your gray, is going to be constrained at each bin. So if, for example, this bin goes up, then the signal will go up too, right? They're perfectly constrained together. I just want to make sure you understand this concept. Sorry, I just kept going. Yeah, I want to make sure you understand this concept because things are going to get complicated very quickly now. So we started just by adding Z to muons to explain Z to neutrinos. The problem is the production rate of Z to muons is 10% the production rate of Z to neutrinos. So what we just said is that, well, we're going to calibrate our simulation with a sample that is produced 10 times less than Z to neutrinos. That means our statistical precision of our signal region is 10 times worse than the data. So effectively, you know, we're doing analyses with 10 times less data. And up until 2015, this is what we were doing, right? We were basically throwing away our data 10 times, you know, 90% of our data, and using Z to muons to calibrate. So, you know, this is not going to get us to this 1% precision that I told you with. It's going to get you, if you extrapolate this to really high missing energy, so like the highest, a TeV, something like 100% uncertainty, right? So it's not, and you know, this gray guy is at 15. So how do we get there? Well, we need to start adding more regions, right? We can add Z to electrons, right? So Z can decay to electrons. Yeah, sorry, and so Z is decays to electrons. So this gets us down 5 factors square root of 2 in our sensitivity, right? This is like doubling. This is going from 10% the data to 20% the data. So now we can at least constrain things a little more. But then we want to go further and we want to add something that's actually powerful. So to do that, I want to ask you a very important question, which you probably asked yourself, which is, do you want coffee or do you want tea? So I don't know if you know what the right answer, but the answer is yes. And this is basically the strategy we have for understanding this, is that we need to not just use Z to muons, right? We need to use something else, right? Something that's more powerful, right? Something that's a little bit stronger than T. So we can use another production that's similar, which is photon plus Fish production. Right? A Z boson and a photon are pretty similar. They're not exactly the same. Question? Oh, get the mic. Yeah.
Actually, it refers to something we talked before about when you said to use the scaling factor R, I think for the control pins.
Yeah.
Yeah. So my question would be, okay. So for the muons, I guess it makes sense to have just the scaling factor over all the bins because, I mean, the efficiency rates are like almost 100% and stuff. But what if we, for example, have something not as muons, but for example, B-jets, and then like, can we then use just a simple scale factor, or wouldn't like this depend on each bin? Because I don't know, you have efficiencies that depend on PT and stuff like this.
Yeah. So all right, at the moment, our scale factor is per bin, right? So
Okay.
every bin here is a scale factor. It's freely floating, right? This bin could go way up, right? This bin could go way down. Your prediction is going to go way up here and way down. right? It's, I mean, really, if you have a bump in one region, it's gonna give you a bump in the other, right? Everything is freely floating for bin. Now, there are things like turn-on curves and other things. These you embed into your analysis, right? So for example, might know that, your selection for muons is biased, right? In the low mat region, which is actually something that's true. So this region, this actually the acceptance, so kind of the rate of selecting muons is lower here than here. So what you then have to do is parameterize a correction, right?
Okay.
And so you actually will correct, you correct for this, this effect, and you basically remove this correction when you propagate this to your scale factor.
Okay.
This function here contains all of those corrections, right? So, and I'm gonna go into some of the details of how we do these corrections, because there's some that are really important. So,
Okay, thank you.
yeah,
Are there people using machine learning to do this?
yes. Yeah, that's another lecture. But if you want, I'm happy to talk about how all of this is all machine learning now. So, or at least a lot of this is actually embedded in here. So muon ID is machine learning based, electron ID is machine learning based. The missing energy, we don't use the machine learning missing energy, but hopefully we'll switch. So I mean, there's a lot of machine learning here, but I think it's we can talk about that later, say after election.
One more question.
Yeah, another question.
I'm seeing you have always struggled to model your background from a standard model, but how you can add how do you do with dark matter to model dark matter on your Monte Carlo simulations?
You make a guess, right? So that the simple answer is you make a guess, but the kind of deeper answer is that it doesn't matter so much, right? We're predicting things, we're trying to get things here where we predict it at the percent level. If you have dark matter, you're looking for just a deviation, right? Any deviation is a sign that there's dark matter. We have no idea what it is. So you make a guess, say, oh, maybe it's like this, and you interpret it. But in the end, we don't really care what our signal is, right? We just care that there's a deviation between our data and our prediction, right? That's, it could be the dark matter. I have no idea how it would be possible. Just, work predicts an excess of 600 GeV. You get some weird bump here. I can't give you a model that would predict that, but I mean, if we see it in the data, then it's a sign there's something weird going on. I mean, I can tell you, like, my thesis was delayed because they're actually in this plot, right? Actually in this plot at 90 GeV, there was like a weird bump. And I spent like 3 months, like I thought I had something. It's like 4 sigma at one point. So 4 standard deviations off from the prediction. And so I delayed my thesis and I wrote like a whole paper on this. And then we got more data and it disappeared. But there was no model. We had no model that could predict that, right? All right, so the thing is, so I said we want to use gamma plus jets. The problem is, and photon and a Z are very similar. Their Feynman diagram is the same, at least with respect to QCD. However, there are some differences, right? A photon is massless, a Z is not. And so in 2015, we started to look at this and think about it seriously. And we just looked at kind of the previous studies that had happened. So these are some of the mysteries we saw in the data. If you look at your prediction, right? So these are kind of the fanciest predictions you could get at the time. They're also still state of the art now. And if you take the data, this is the left here is Z to leptons, right? This is all Z to electrons and muons merged. The right here is photon production. And if you compare the fanciest data or the best, like cleanest data with the fanciest simulations, you see that your predictions are off, right? Rather substantially. And more importantly, your photon prediction, right, in this region is different than your Z prediction. So now we're going to make the claim that we can use photons to predict Z. But then when we looked at the data, right, our prediction for photon and Z were quite different, right? Using the same simulators, right? The same setup. Question?
How do you determine your bin size?
So the question is,
Just repeat it.
yeah, the question is, how do we determine the bin size? And that the answer is it's just based on the number of events, right? It's how we want to make the plot work. You can use, I mean, there's a lot of subtlety here. The one thing I will say is if you're making experimental plot, the binning you should always choose is larger than the resolution of your detector. The detector resolution for missing energy is on the order of 20 GeV, which is way smaller than every bin I'll show in this talk at least. The resolution for muons is like a few GeV, so it's much smaller than these bins, right? So, yeah. All right, so we had a plot where photons predicted differently than Z, and then you can take the ratio and look at your predictions, and you get a plot like this. So this is the ratio of photon Z or Z to photon production. And you can see your data looks like this, and your predictions look like this, and they're off by 10–15%, which is the same order as the disagreement in our simulation. So we needed to come up with a way to fix this. And this was not, people have been thinking about this for many years. So somebody actually here in Les Houches, they started to solve this problem in 2015. And in fact, if you had looked in the literature, it's actually found that somebody actually solved this problem, had been actually solved in 2006, before the RC was predicted, but it was running, but it was kind of lost in the literature. And in 2016, they kind of dug up everything, put it all together, and actually at the Les Houches 2015 workshop, they actually came up with a solution that effectively, what I was showing before is kind of this orange one. This is the ratio. They were able to go from this down to these points. And the way they did this is they had to add higher order electroweak diagrams. So what do I mean is that if you're trying to predict Z boson production, or for that matter, W boson production, you need to add crazy diagrams like this. So you can imagine, imagine how you have a W here and a Z here, right? And it radiates two jets, right? This is a pretty serious diagram. If you want a good homework problem, but yeah, so the point being is that the people were finally starting to do next to leading order electroweak fractions. And this was like essential to actually understand this ratio of Z to photon production. So what we did is we found all these papers. In fact, we didn't even know about the study when we did that. We took the papers there's a bunch of papers in 2006 that did the next to leading order corrections. And so we just combined them, and suddenly we were able to get actually really good modeling of the Z photon ratio. And now we're at the point where if we propagated our theoretical uncertainties into either Z boson production or photon production, we were at the point where we were getting to the 1 or 2% level, right? So we were getting to really high precision. The problem was we didn't know how to deal with these uncertainties. So if you calculate this diagram, right, there's a bunch of choices in your scale, right? Your resummation scales, your renormalization scales, etc. Your choice of alpha sub s. And if you do this calculation, you also have to make scale choices. And we can define our uncertainties, right, based on the scale of our calculation. The question is, if you now calculate this guy, you calculate this guy, and then you take the ratio, how do you correlate the scales between the two, right? So this has some implicit strong coupling scale. This has some implicit strong coupling scale. And you want to equate these two when you do the ratio. And it turns out, I mean, people have thought about this, but there was really no common prescription. And, the kind of, well, I'll get to how we solved it. But at the time, we didn't really know what the right solution was, so we took a guess, which was to take the scale uncertainties, right? And first take it in the fully correlated scenario. So that would be the case where we have either photon production or Z production. If we vary the scale of, let's say this is the strong coupling scale, we vary it up, we get a modified spectrum as a function of PT. And we took this fully correlated, right? So if the photon scale went up or the Z scale went up, it affected the cross-section at the same rate of the photon and the Z. So what this means, right, is that if you vary your uncertainty, right, it all goes up in a consistent fashion. Now, in reality, this is not the case. The diagrams are not the same for photon and Z. So we just invented a decorrelation strategy where we decorrelated these guys so that we have now not just one correlated uncertainty, but multiple uncertainties where you vary the scale up of one, and then the scale of the other one. So let's say this purple is an uncertainty will be different, right? So the purple will be a smaller uncertainty. And then you can imagine then just from this matrix, right, you're going to have two uncertainties now. So you have a scale up for one and then a scale up for another, which would be your purple and digestion. Yeah. Question?
Yeah, I kind of lost you a little bit here, I think. Are we talking about theoretical uncertainties?
Theoretical uncertainties.
Okay, and why do those exist?
If you do a calculation, right, there's always some assumptions you make when you put the calculation. The classic assumption is that what's the value of your strong coupling, right? So you have to choose a scale for the strong coupling, right? And so whenever you calculate a diagram like this, you make a bunch of choices. The strong coupling is the choice. There's also the coupling, the resummation strong coupling, which is if they're factorized, right? So you have two strong couplings. And typically we actually vary the strong coupling scale, right? So the scale that we choose for our value, we vary it at different energies. And that defines uncertainties on our calculation.
Okay,
Right.
so we're not talking about like the addition of higher order terms. It's just in these
So that-
next to leading order
No,
terms.
so these are all, I mean, so this is for, like, when I talk about this diagram, I'm talking about all the diagrams,
Okay.
right? So, you know, you're summing these, right? In the case of low energy, you're summing these to infinity, right? You're doing a resummation scheme, right? So I'm talking about the choice of the strong coupling in all of the diagrams, right? Correlated, right? Combined. And there's a few of these arbitrary choices, right? And so whenever you do a calculation, you have a bunch of arbitrary choices that are in there, which are typically your strong coupling scale or your strong couplings scale, because there's a few different couplings that are factorized. And so what you do then is you vary these separately. And every time you vary a strong coupling, you get a modification in your production, right? So your PT spectrum is going to change. So I varied my strong coupling, right? I put alpha S from the ZMAS scale to double the ZMAS scale, for example. And this will change the PT spectrum of all the diagrams. So the relative contribution of the diagrams is going to change, right? And you're going to see that when you sum over all of them and you predict the PT spectrum, you're going to get something that's modified, right? Now the question is, right? If you make an uncertainty choice, like a strong coupling variation choice for one set of diagrams, like the Z boson, does this apply to the photon, which also has a strong coupling assumption? Right? Are these the same coupling? Are these not the same coupling? And this is the question we were trying to answer, right? Can I say, oh, my strong coupling, right, for the quark interaction, when I vary the scale choice, my uncertainty, is that the same for a Z boson and a photon? And the reality is it's not the same, right? The diagrams are different, right? So you can imagine, right? Right, so photon, right? Like this would be your leading order diagram. But yeah, so this would be, say this is a photon. You can imagine, right? So let's just take a next to leading order diagram. So I'll just take a ridiculous one, just to make it easy to draw. So actually this one is not allowed. Sorry. So, I mean, the idea here is, so let's just take something kind of typical. So imagine you have photon production like this, right, with the jet. And then you want to equate this to like the Z boson production with the jet. So it turns out that when this jet gets close to this photon, right, when these guys get close, the diagrams, the production diagrams are very different. And the reason is simple, is that this has mass 0, right? And this has some mass, right? And so this you can imagine having basically a collinear, almost collinear radiation. Whereas for this guy, there has to be some momentum here, right? So that you have to have a lot of momentum. And so this diagram will be different, right, in terms of the momentum transfer. So now I make a scale choice, right, in here, right? So I put some scale choice, right, at some scale for the strong coupling. It's not clear that in the case where the jet is radiating close to a Z, the scale is the same, right? And you have to basically go diagram by diagram and look at your assumptions about the scale to actually, come up with a scheme to vary these uncertainties.
And then, yeah, just a follow-up question. So why wouldn't the off-diagonal terms be functions of that scale?
Yeah, so the off-diagonal terms are a function of the deviations.
Okay.
Right, so if you say, well, look, in this regime, right, these things are going to be different. Well, if they're going to be different, then they're not going to be correlated, right? Fully correlated. So you're going to get additional terms. You're going to get these off diagonals, right? So what's going to happen is that since they're not correlated, you're going to split and get multiple uncertainties, right? Is this clear? This is kind of the whole crux of. It's kind of difficult to, if you write down all the diagrams for Z boson production at like next to leading order or next to leading order, you start ending up with like thousands of diagrams. So we didn't go through all of these one by one and check, right? But we tried to come up with kind of envelopes for how they would behave. Question?
Yeah, so once you maybe set, for example, the angular separation between the photon and the jet,
yeah,
I don't know, let's say whatever, in your simulations, then basically you can look at the ratio as a function of mu, and then basically this ratio vary with the scale. No?
that's exactly what we did, right? So that's exactly the whole point of this, is that we're looking at these ratios, and they're just going to be the eigenvectors of this correlation matrix.
Okay.
Right?
Cool.
So, right? So all we're doing is we're just taking the eigenvectors of this correlation matrix, and this defines uncertainties, and the uncertainties are all parameterized as a function of the ratio, right? So, all right. So I showed you the simple case of one photon and one Z, right? And so what we did actually, in the first time we did the analysis, was we didn't actually know what the appropriate decorrelation was. So we just kind of made a guess. We knew what the uncertainties were if they were fully uncorrelated. And so we made the assumption that the uncertainty on the ratio is going to be sufficiently decorrelated that the uncertainty on each process was going to be the fully uncorrelated uncertainty scale. And this defined an uncertainty on the ratio. So so what we did was we basically arbitrarily adjusted this until it was at the size of the uncertainty on an individual process, right? So it's equal to the uncertainty propagating an individual process as if it were uncorrelated. And it was not well motivated, right? We kind of pulled this out of a hat because we wanted to do the analysis. But we also made this very clear that this is an open problem and that somebody needs to solve this. And we also had the same thing. So that was for the QCD uncertainty. The higher order electroweak corrections that we had added, we had the same scheme, right? And they're different in the sense that QCD kind of varies your spectrum by a constant value across the full PT range, whereas electroweak corrections tend to turn on at very high energies, mostly because the electroweak bosons are heavy, so high energies are more important. Right, and so we had the same kind of scheme where we had a separate, we propagated a separate next to leading order electroweak correction and a separate next to leading order electroweak correction for the Z and for the photon. And we treated these as two uncertainties that were uncorrelated. But we posed this as a major problem. And we put out a result. We did a first monojet result. We were able to get that to that precision. I'm not going to show it because we kept going. And we said, look, we're stuck. We need to solve this problem. And so at this point, we realized we in addition to doing a photon to model the Z boson, we said, well, we might as well use the W boson to also model the Z boson, right, in this case. And so we ended up with kind of a big simultaneous fit of all of these three, right? So now we have the W boson is predicting the scale factor for the Z. The photon is predicting the scale factor for the Z. We also had the W, we already had it because we had W predicting W as well. So the W is predicting W and Z. And so now we have this big fit on all three of these guys all together in some big simultaneous fit. And just to be clear, right, we're doing the same scheme where we have a single bin is constrained across all of these guys. So we had this setup, And we had uncertainties on these ratios. This is what they look like, the time. And you can see we had a correlated and uncorrelated uncertainties. So the orange are the uncorrelated. So basically every bin could move up and down on this ratio. And then we had correlated, which are these green guys. So when you fit these ratios, this could move like this, and then each bin could move. And this is separate to our scale factor. So right, what this means is that, right, if you look at the ratios, right, this guy could move up, but your prediction wouldn't change, right? So there was flexibility in this fit for it to move up and down, but the prediction wouldn't change. If this moved up and then the scale factor moved up, so it could still, like the whole thing could move up and down, but you gave it basically wiggle room between each of these distributions. So it's complicated fit. So we had uncertainties like this. And then we basically got a result, actually it came on Christmas. And so we ended up with these higher order corrections, a scheme for higher order electroweak correction. And Passerini and like all the I'm sure you guys know all this. So what they did actually was they decided to, in calculating this ratio, either photon to Z, or now we had added W to Z. They basically went through diagram by diagram and varied the scales and asked the question of, can we correlate these or not, right? And so they went from this just, oh, you know, 2D matrix, right, to a much larger matrix, where they went through all the different subtle corrections. So you end up with these various different next to leading order corrections for various different diagrams. They have great names like delta 1, delta 2, and delta 3. And so here's kind of the idea of these corrections. So this is the ratio of higher order corrections next to leading order as a function of the PT of the boson. And now we have Z, W, and photon all together. And so you have these ratios. And you can see that, you know, the corrections, if you propagate these corrections, they're almost all the same, right, between these different processes. If you propagate these corrections, they're almost all the same. But here for these delta 3, right, you see that the photon changes, right? And in fact, this low energy stuff is actually this diagram here where they start being correlated, right? And here's the same thing. If you go, this is one loop, this is two loops, right, next to leading order. And so you can see the diagrams are the variations are quite similar across them. In fact, if you go to higher orders, I think it converges. They get closer and closer between these different processes. Higher order and QCD. So this is the QCD next to leading order. Here's the electroweak next to leading order. And you can see actually here the deviations are much larger. So you see actually at low kind of energies, they're similar. But when you get to higher order energy, so these are what we call the electroweak pseudocol corrections, because you can write this in terms of pseudocol. You can see that if you correct a Z boson, it can have a large correction, but it will be different for the W, right? And it'll be even more different for the photon, right? And the higher order corrections change. So you could go ahead diagram by diagram and factorize these as these theories did. You can also ask questions about the photon content in the proton and how this impacts your calculation. And you end up with this list. So this is actually what we use when we run. They ended up with it's like 25 by 25 matrix, correlation matrix of all the variations you can do in the diagrams for these ratios. And these are the eigenvectors. So they have all these interesting names that you can kind of guess. And they're approximations, right, of what we actually are doing. And then they give us a correlation scheme. And so we took the analysis and we were able to do that. And so our hand waving, yeah, question?
Sorry to interrupt, but just quick. So in the 2 slides before, I think when you showed the calculations for the Z plus jet, so would it Yeah, exactly. So would it make any difference between a 4-flavor scheme calculation or 5-flavor scheme calculation?
Yes, all of this would make a big difference. So
Okay.
yeah, 4 and 5 flavor. So for actually for the electrolyte corrections, no, right? Because this is electrolyte corrections, but for the QCD corrections, it makes a difference, right? So whether you add the mass, the B quark mass or not, I mean, it's built into these corrections here. I mean, there's a lot of assumptions here. You probably, if you read these carefully, there's probably a 4-flavor, 5-flavor correction. Maybe this gamma, no, it's not. Anyway, it's in here for sure. So in the end, we were able to come up with a scheme of uncertainties that look like this, right? And just to give you an idea, like if we just took kind of the uncertainties on the processes themselves, they were ordered 10%. But with this scheme of uncertainties, actually going through diagram by diagram and understanding the correlations of the scales, the variations on the order of 1%, right? So this is a zoom in, right? This blue box is the range here, right? So you're really zooming in. And so what did this do, right, in terms of growth predictions? So this is our old analysis scheme. And so here are our data predictions. So what we can do is that to test, before we even look for a signal, right, we can take the Z lepton photon ratio, we can take the W lepton photon ratio as a function of recoil, right? And we can compare our predictions. This is kind of a validation. And the strategy we always did is to take the ratio, look at the data points, and look to see if they were mostly in the gray region, right? And so we did this and we thought, oh, well, our uncertainty is covered. But now we got new predictions, new ratios, and we got down to this. And you can see, right, the points are mostly in the gray. And let me just, this is an old analysis. So let me just show you the new analysis. So this is, I'm gonna go to the new, this analysis came out 2 weeks ago. This is where we currently are. So you can see now we have kind of really high precision and the uncertainty, we're well within the uncertainties, and actually the agreement is almost 100%. This is kind of a triumph. I mean, to run these calculations, we're talking about years and years of calculations, but years of computing too, right? This is not like a light statement that you can make a plot like this and have the ratios agree to a few percent all the way out to its UV. So this was a dramatic improvement in how we did the analysis. And so then we finally did the analysis. And so we had our Z, right? Now we added W. We went from 60% to 40% uncertainty at TeV. We added the other W to muons, W to electrons, right? This brings us down to 30. Then we add the photons drive everything. And then we got down to 15% uncertainty. And every bin here, right? They're all constrained. It's the same scale factor, right? The only thing that's happening is that this guy can wiggle within some uncertainty, but this guy can't, right? So these can all move within some different uncertainty scheme, and the uncertainty is all in the ratios. So you end up with this fit. It's about 400 parameters in terms of uncertainties. It only takes about 5 minutes to run. It's not so bad. And so then you end up with this result. So finally, you get a result like this. Do I zoom in on it? No. So you get a result like this, and it's kind of hard to read these plots. So when I look at this plot, I mean, I don't look at the top plot really. I just look at the ratio. And so what you care about is the ratio. So in this case, this is the blue points and how it predicts with respect to 1. And then, in fact, we also have this written in terms of the uncertainty on the prediction. And so this plot is actually, this is an old analysis. This one's a little bit worrisome because you see that there's a kind of a trend. So there's too many data events, right, at low met. And then the agreement's quite good. So the variation within the uncertainty is close to 0. And in fact, you have a little bit of a deficit here. So if I look at this plot, I see this trend and I'm like, something's wrong. It turns out that this was wrong. There was actually an effect in modeling the turn on, and it actually had to do with the modeling of this turn on with respect to this. There was an effect, and we fixed it a few years ago. So there's a lot of subtlety in these plots that I'm kind of hiding. So this is basically the analysis though. We're using every production process we can think of to predict C2 neutrinos. And this is how we got to our tiny uncertainty, right? And this is how we got this really good prediction. However, oh yeah, sorry. The however is kind of cool. And if you just want to see how you write this in terms of a fit, here's your fit likelihood. I won't like walk through this because I think it's straightforward. Well, you guys can stare at it at your own time, but effectively we put a binomial uncertainty on all of the bins, right? And then we propagate the scale factors through. So the Z neutrino is propagated, the scale factor for that is in every single final state. And each box here is a different distribution. But we can talk about that later. Okay, so now we can actually look for dark matter. The way we do that is we look for a deviation in the slope. By the way, I showed CMS, but Atlas copied our approach. Atlas does exactly the same now. It's a copy. I'm not gonna lie about it. Oh, they actually, Atlas can't do gamma plus jets. They're not good enough at it, so they just removed it. And then they complain and say, CMS, it's impossible that you do this. We don't believe us. But that's a fun story we can we can talk about that at then. So the one thing that, so now you can start to look for dark matter. And their general rules of thumb, as you vary the mediator mass, right, the slope gets flatter and flatter. And basically what you now want to do is take any deviation between data and simulation and look for a signal. And so now we can start to interpret this. This is the current CMS result. There's no single plot, unfortunately, so you have to look at the plots for different years and look at the predictions. But suffice it to say, right, things are moving pretty close to 1. You don't really see any deviations. So there's no real sign of dark matter. Some people might see this at the end and get excited. I'm not excited. Now, the interesting thing is that when you do this, you start asking what impacts your sensitivity of your analysis. This is a sensitivity plot. This is the kind of plots we make inside the collaboration where we vary our uncertainties. So this is the top 30 uncertainties. There's like 400 of these. And then this thing here is the impact of it on your sensitivity. And basically the top 10 uncertainties all contribute about the same. And they come from all over the place. Right? The top uncertainty is the electron efficiency. So now we're looking for invisible signals, but the electron efficiency turns out to be the most sensitive uncertainty in this analysis. And that's basically because we're pulling in like, 80% of our data, selected data in CMS is going into this analysis. So we're sensitive to every single thing, right? The second one, trigger efficiency, you can talk about that. The theory uncertainty, the first one that pops up is in the 4th position. When we did this the first time, the theory uncertainties on the ratios were the dominant uncertainty by far, right? And once we understood those and we got this paper, we were able to bring these down. And now there's kind of a fight of what uncertainty is going to be the dominant one. But these are all uncertainties. All of these guys are uncertainties that we can continue to bring down. And just as a note, right, this analysis is never going to be limited by systematic uncertainties. Right, you can add more data to all of these regions and it will improve your sensitivity. So you can continue to run this analysis until the end of time, right? And it will get more sensitive. There are some limitations, but they're not so many. So now we finally get to interpret it and actually interpret it in the context of dark matter. The typical way we do this is we make some assumption about the Lagrangian, and then we make plots like this, where we search for a mediator mass, and then a dark matter mass. Dark matter is, so we need, the mediator has to decay to dark matter. So we're typically sensitive below this line here, where dark matter mass is equal to 2 times the mediator mass or less. Go off shell, but your sensitivity is not great. And we'll talk about how to go and probe this region in the next lecture. So, all right. So what did we do? We tried coffee NT. We also added a secret mixture of higher order corrections. And between all of these, we were able to go from, what was very large uncertainties down to something that was very constrained, right? All right, so now I want to really talk about interpreting. This could be the rest of this talk. The Three Musketeers play a very important role that I'll get to. And just to kind of put 6 years of work into one slide, for many years, people were kind of interpreting this in the context of effective field theories. And the nice thing is that, you get rid of the mediator, you get rid of coupling between a coupling to the standard model of the mediator and a coupling to dark matter of the mediator, and you just absorb it into one value, which is a coupling. But this breaks down, right? If you try to do an EFT calculation at low energy and high energy, it will change, right? The distributions will change. You need to put in a mediator assumption, especially at the LHC when you're probing high energies. I won't go into more details about that, but suffice it to say that in LHC round 1, all they did was all of the analyses were done like this. And they went as far as to write down every possible combination of EFTs. They made this menagerie of stuff, but it was kind of a mess. So we got rid of that, and we wrote a bunch of papers on how to do this with simplified models. And basically, the way we did this was we wanted to ask the simple question of how can we make dark matter interact with matter in the simplest way possible. And so we added a mediator in dark matter, and then we added a Lagrangian where our mediator couples to dark matter with some coupling, right? And then we wanted to ask, well, what are the kind of mediators we can do? Well, we made the assumption that this could either be spin 0 or spin 1. So we add a spin 1 coupling, which is uniform coupling to either quarks or potentially leptons. But the idea is to have a uniform coupling to the standard model. And with spin 0, we put a Yukawa coupling to the standard model. Right? So it's about as simple as we can do it. And this gave us production modes that we can then use to actually search for dark matter. So with spin 0, this is like Higgs production. The dominant production is through a top loop, just through gluon fusion. Right, for spin 1, the dominant production is just like Z boson production. It's just quarks radiating a jet, producing a spin 1, or often we call it Z prime mediator. Then the differences between these is, well, this is like a Higgs search, right? So the cross section is large. Sorry, the cross section is small, but the PT is large. This is like a Z boson measurement. The cross section is large, but the PT spectrum is not as hard, right? And that just depends on the initial state, right? To get the gluons, well, to have a top loop, you get an enhancement of higher energies, just coming from the fact that the loop is resolved. Okay, now to basically preserve generality with direct detection and indirect detection comparisons, we also split these guys a little bit further. We add a gamma 5, so you can get either a vector or an axial vector. We use just the pure vector or pure axial vector in terms of our interpretation. It's not because we think the physics is like this. It's because it makes it kind of, these are the extremes for comparing with direct detection and indirect detection. And more importantly, right, for collider physics, it really doesn't matter, right? The production modes are almost exactly the same between these two, vector and axial vector. And actually with scalar and pseudoscalar is quite similar, right? The pseudoscalar, you get an enhancement in total cross-section, but your differential distribution is the same as the scalar. Right? And this allows us to compare. And we can then compare these. So the production modes, so this gives us the 4 models. The production modes are the same for axial, vector, pseudoscalar, and scalar. And then we can compare these with direct and indirect detection. So with the collider, the vector and axial have very large cross sections. The scalar have kind of, it's like a Higgs measurement, so they have a relatively low cross section. The pseudoscalar is better than the scalar, just there's an enhancement. There's a lack of cancellation in the diagrams. But then, we want to compare this direct detection and indirect detection. And so with direct detection, Well, the vector mediator is very powerful. This is what we call spin-independent direct detection. When you have an axial vector mediator, right, this is what you call spin-dependent direct detection. And so everything is suppressed, right? You're sensitive to the spin. For a scalar mediator, you can also use direct detection, but now your diagram is loop suppressed, right? So you have it, the scalar will couple to gluons through like a top loop. So you don't have a direct coupling. Well, the direct coupling is Yukawa suppressed, right? So the dominant diagram comes from, let's say, like a top loop. So the cross section is not so great. And for pseudoscalar, it's heavily velocity suppressed. So don't even try to use direct detection for it. But what we can use is indirect detection, right? So this is how we interpret things. And the best way to think about this is in terms of the Three Musketeers, right? Because you know there's actually 4 of them, right? There's like the Three Musketeers, Porthos, Athos, and Aramis, and then there's D'Artagnan, who is not a musketeer, but he's like the coolest one, and he's always there.
Yeah, a question on the slide with
Yeah.
the pseudoscalar, I think. In the last one, you got an asterisk that there was a paper that claims otherwise. For the, everything
Oh
else.
yeah, this guy.
Yeah, so I guess I'm wondering what's going on with that.
Yeah, I think this is at this point, this claim is done. So
I see.
yeah, so I don't know, maybe Marco, no, I don't know who wrote this. I've forgotten this paper. But there was a claim that it was not velocity suppressed, and that you could in fact be sensitive to pseudoscalar. I always put this in my slides, but there was never a debate about this, and people come to an agreement that it's typically not the case. Right?
Okay.
You know, if you were to calculate these, right, these are on the order of like 10 to the minus 45. So I don't have the plot on me, but basically this is like 8 orders of magnitude smaller. If you just do the calculation with like a top loop, and then you assume some thermalized velocity in the solar system. So.
How does the region of parameter space probed by collider searches compare to the parameter space probed by indirect and direct detection?
Yeah, that's where I'm going.
Okay.
That's the end of this talk. So, all right. So how do we interpret these results? Yeah, I have to start making decisions. Oh, the only thing I want to mention is that the other thing we made when we made the simplified models is that they don't mix with the photon of the Z, right? This is a choice. It doesn't really impact the results that much, but it does become an issue when you go to lower energies. So people often talk about the dark photon, and then I'm talking about this vector mediator. The only real difference is that one mixes with the photon in the Z and the other doesn't, right? And from a collider physics aspect, it doesn't really change things that much. It changes the cross sections a little bit. And so, another question that you guys can argue about with yourselves is how do these things get masked? I won't go into that. And just for reference, right, here's the widths. One thing we do think, we try to take we typically take a very large dark matter coupling, right? So we take a dark matter coupling of 1, right, because it's a nice number. And then for the couplings to the standard model, we typically take a coupling that's of order the electroweak coupling as a reference. So we take 0.25, right? The standard model electroweak coupling is order 0.3, right? And so then you can just get your widths, right, from calculating this. And of course, right, the width is 0, right, when the dark matter, the decay of the dark matter is, the mass of the dark matter is 2 times it is greater than the medium mass. And so this gives us our plot, right, which I showed you before, as a function of mediator mass, dark matter mass, and you have on-shell production. And here's actually, these are the most recent results from Atlas and CMS. They both came out a few weeks ago. And so you can see CMS is, what you want to compare is in terms of, as a collider physicist, I look at the expected sensitivity first. So you want to see how far a mass reach you have for expected sensitivity. So CMS is at 2.2 TeV, and Atlas is at 2.1. So this is a win for CMS. I mean, this is like a huge 2.2 and 2.1, right? The cross section is 1 over mass to the 4th, right? So it really means you're more sensitive. But then you also want to look what the observed is. And so you can see that CMS has an excess. They actually exclude only to masses of 1.9 TeV. And Atlas has a slight excess, and they exclude at 2 TeV. So if you want to read into this, there's maybe a sign of an excess in the tail of the Met distribution, but it's the way you want to interpret it. It's 1.5 sigma, and it's not enough to get really excited about. Yeah.
Is this your highest precision for the run 3, or are you doing?
This is run 2. This is like the best result that came out a few weeks ago.
Okay. But I mean, do you still put that plan to push more analysis? More
Yeah,
data
there's always.
before the run 3. I mean,
Oh no, so this is the final result before run 2. So
okay, yeah.
don't expect a result for this for another 2 to 3 years. Right? So,
I'm sorry, I'm not seeing, how I'm seeing an excess here. Can you go over that again?
yeah, no, this is an art form. It's not an art form, but it's so you're familiar, are you familiar with these Brazil band plots?
Yes.
Right? Yeah, you guys. So basically, right, the green is the 1 sigma region, the yellow is 2 sigma. If you have an excess, that means your exclusion is not going to be as far as you're expected, right? What you care about is the expected result, right? So if I have a deficit, I'm going to be able to exclude more than my expected result. If I have an excess, I'm going to exclude less than my expected result, right? Typically, I'm going to be somewhere in this Brazil band, right? Because things don't fluctuate too much. So I look at the expected, right? See where the sensitivity is, and then I ask myself, well, where's the observed? It's a little bit lower than expected. That means there's a small excess. In CMS, right? We didn't use Brazil colors, but we put a 68% confidence line, which are these dashed lines. So that's the equivalent of the green band here. And so what you see is the expected is here. So a 1 sigma deficit would be here, right? So you would exclude more than you observed. 1 sigma excess would be here, right? And then the actual observed is a solid line, and you see we exclude even less than that. So,
I see.
yeah. Question in the back? I'll just repeat.
Okay, just say it and.
Yeah.
Yeah, so I wonder, these access, at least in this form that you are showing, would span very large mass range, right?
Yeah. Yeah, the excess here, what do you mean? It goes, it changes by like 300 GeV, right? In terms of
I mean,
interpretation.
like the vertical axis, so the dark matter particle mass.
Yeah, on the vertical. Yeah. So, the actual, so we make this plot, right? But the production mode, the distributions of these are roughly the same as a function of dark matter, right? Because when the dark matter is light, it doesn't really matter what the mass of the dark matter is. The decay is going to look exactly the same. So these lines are like almost vertical for a reason. The reason they curve over like this actually comes from the width formula, right? There's a mass dependence, right, in this term of the width, right? Z is, gosh, I thought I wrote this. Z is the mass over the mediator mass, right? I'm going to skip the next 80 slides and just go to the kind of the punchline. So, yeah, so let me skip to.
You can also resume tomorrow.
Yeah, I can go through this tomorrow. I have plenty of stuff. So, all right. So yeah. So the question was, how does this compare to indirect detection? So this is the monojet search, right? Or sorry, direct detection. This is for a vector mediator. And so you can see direct detection is way down here. The monojet search is right here. This is an old result. I'll show you the newer result. Doesn't really change very much. But kind of the important thing is that for low mass, right, the monojet search is actually more sensitive than direct detection, assuming this vector mediator. How we translate this, I'll also talk about in the next lecture. Here's also here's the axial vector mediator, which is now spin dependent direct detection. And here we're actually way more sensitive, right? So here's the direct detection line, right? So you exclude above here. And here's the current, this is the monojet search, this red line. And so we exclude, well below spin dependent direct detection. And more importantly, we're actually below the neutrino wall, right? So we're beyond the sensitivity of direct detection. So this is the importance of splitting between vector and axial vector mediators. If you can imagine some mixed current. And just to skip to the scalar and pseudoscalar interpretation. So here's the scalar pseudoscalar interpretation. So here's the red line here is the monojet search. And here's the thermalized cross-section. So this is for a pseudoscalar mediator. So this is the indirect detection. So here's like your Fermilab results are up around this green line. This is the relic. So this is actually the Fermilab result. I thought it was the relic. This is the Fermilab result. And you can see the galactic center axis is up here for a kind of simple pseudoscalar or an axion like particle mediator. We exclude it by several orders of magnitude. And here's the scalar direct detection. So scalar direct detection, here's kind of the current spin independent direct detection mediators, and here's the scalar. And we exclude we're competitive, but not as, the direct detection is still a little bit better. Right, so that's how it compares. And I'll go through how we actually make these plots in the next lecture. All right, so I just showed you monojet. But I'll talk a little bit more about how we split this into other things like mono vector boson and mono top, mono B, and even other things. But kind of the key thing here is that understanding the missing energy distribution is the key. So yeah, in summary, in the 19th century, dark matter was a problem, and now it's a problem again. And to search for dark matter in its simplest form, we just look for missing energy at the collider. And we interpret this in the context of spin 0-1 mediator. The first dark matter problem was resolved by an accident. And so hopefully, or perhaps the new one will not. So I wanted to come up with some discussion questions that you guys can think about. So here's a good question we can talk about tomorrow is, what are some bad things about simplified models? There are really a lot of them. And another question to think about is, can this control region method work if there's signals in the background, right? And this is a question that people ask me all the time, which is a good one. So yeah, we'll see you in the next lecture. So I'll talk about kind of go into more detail about direct detection and how this plays a role. Thank you.
Great. Thank you very much, Jay. If not, okay, so see you this afternoon at 5:30 p.m. for the long show.